Good afternoon, everyone. My name's Tucker, and today I have with me Alana and David, and we'll be presenting to you our analysis of the NCAA's March Madness Tournament Challenge. Quickly going over the format for our presentation today, we'll start by giving you a background on March Madness itself and how we formed our business problem. We'll then give you an overview of the data we had to work with and the accompanying analysis in our studio. Finally, we will discuss our model, outcomes, our completed bracket, and opportunities moving forward. Now, beginning with our introduction and overview, March Madness began in 1939 and is a college basketball tournament consisting of 64 teams competing in a single elimination style playoff comprised of 4 divisions. For a team to win the title of national champion, they must win 6 consecutive games against the best competitors around the United States. Furthermore, the maps on the right side of the slide represent which areas of the country are viewing their respective teams and work to show the general popularity of the tournament itself. This has led us to defining our business problem, which is that we aim to create the best analytical model so as to predict the winners of each individual game and the overall tournament. Although, given the current impact of COVID-19, we have decided to pivot and are looking to predict the outcomes of the 2019 tournament, as this current year has been canceled. Furthermore, this poses a valid business question as the datasets are both extensive and the financial incentives are lucrative, as a perfect bracket will net a $1 billion prize. This is because the odds of a 100% correct bracket are 1 in 9.2 quintillion, making modeling this problem exceedingly difficult given these odds. Furthermore, sports analytics have grown into a massive industry, with this tournament forming one of the largest betting events in sports history. Therefore, there is significant business incentive behind creating predictive models regarding the March Madness tournament. Additionally, we've established 3 benchmarks to measure our accuracy against. Obviously, the ideal goal is to achieve a 100% prediction accuracy, but this is just not realistic for our challenge. A realistic benchmark would be achieving at least a 50% correctness rating, which we coined the guess rule. Our final and more challenging goal we decided upon was founded by aggregating all the March Madness data post 2003 and making predictions solely based on choosing the higher seed to win games. This yielded an accuracy of 67.71% and formed the benchmark for our project moving forward. I'll now pass it on to Alana, who will discuss the data set that we used.
Thanks, Tucker. So just to quickly outline our process, we first sourced the data, then aggregated it, tested hypotheses, created models, and then finally analyzed our findings. Jumping right into the data sourcing, the event data was available from the Google Cloud NCAA ML 2019 men's competition on Kaggle. These statistics reach back to the beginning of the March Madness tournament, which is almost 80 years ago, and they provide extreme detail on each game. We narrowed our training down to the 2015 to 2018, attempting to predict results for 2019. From this, we used regular season statistics for each team in each year to predict the outcome of that year's tournament, and then extrapolated it to predict the 2019 March Madness. With cleaning our data, we consolidated the wins and losses over the selected limited number of seasons and created various ratios. We then compared it to the statistics on the NCAA's website for a random set of 50 teams for validation. Some of the online data included aggregated statistics for both the March Madness and the regular season, so we had to manipulate our data set. We then looked into analyzing the effect of a team's seed on their win percentages. Our null hypothesis was an inverse relationship indication that the lower the team's seed, the greater the win percentage would be. We did this to ensure that we were approaching our problem with a fundamentally sound base of knowledge that was validated through testing. The outcome of this analysis was that the seeds are very influential in determining win percentages as well as tournament success. This aggregated data was then exported for our use in R. We created a number of different tests on the data, and on the slide we have included a little portion of our code, but I'll now pass it on to David, who will discuss our analysis a little bit further.
Thanks, Alana. So to reiterate, we've used the 2015 through 2018 data to train. And our first step in the analysis was running a forward selection and rapid miner. Although this yielded a result that 93% of the variables would be necessary to retain over 90% of the variation within the data, therefore we proceeded testing with the full data set. To build our model, we leveraged 7 different machine learning methods, including quadratic discriminant analysis, k-nearest neighbor, and the others illustrated above. We were fortunate in that we had a clean, well-aggregated data set free of missing or incorrect values, which allowed for us to quickly test many models. In addition to testing different types of models, we also tested different parameters such as the neural network's hidden values and the k-nearest neighbor k values as displayed above. Furthermore, an EDA analysis illustrated significant outliers in our data, but after further investigation, we realized that these outliers were represented mainly through high-ranked teams such as Duke or Kentucky, who are perennial favorites. Furthermore, significant autocorrelation was identified due to groupings of data and games. Therefore, we worked to randomize the data points to eliminate some of those variants. Finally, the talent disparity seen in the data led to skewed distributions for many statistics present in the data. At this point, we then decided to analyze our various models by testing different sets of the data. With this, we split the data into multiple subsets, including the first 5 variables for each team, the first 10, first 20, and only seed. From this, we were again unable to reach the accuracies of the full data set, which we explain in a few slides, but did come away confirming just how prevalent seed is and validating our continued approach using the full set of variables. I'll now pass it back to Tucker, who will discuss our model results.
Thanks, David. Now, after manipulating our various models and going through an extensive trial and error period related to variable use and design, we've been able to reach a maximum accuracy of 71.64%. The top and bottom 3 models and their accuracies are displayed above, although these accuracies failed to take into account the interdependence of games in the March Madness tournament, and therefore have artificially inflated our predictions. Therefore, after taking into account interdependencies, we've reached an accuracy of 62.29% using the neural network model. The next step we took was to apply our neural network prediction to the NCAA bracket to visualize our results, and you can see here the outcome of the East and South quadrants, followed by the successive results of the West and Midwest, and finally, our slightly sad Final Four and championship results. Now, as you can see, the dependency of results begins to compound, therefore drastically affecting our model's performance in the later rounds of the playoffs. Now, given our results on the 2019's tournament, we recommend moving forward with continued testing on the neural network model, in addition to incorporating more width and depth in regards to variable use. Additionally, ambiguity must be reduced going forward, which we'll give suggestions on in a few slides. Now, after completing our 2019 tournament prediction, there are a few key learning points to move forward with. Our initial challenge was regarding what data to use to predict. This was both a blessing and a curse, as the data available is extremely extensive. Furthermore, it was a continuous challenge to overcome the interdependence of the games, as well as difficult to factor in the model. Finally, the highly ambiguous nature of the tournament made it hard to reach our prediction accuracies and goals. Therefore, moving forward, we recommend to dispel some of this randomness by looking to factor in more data. Specifically with neural networks, this will help improve your accuracy by trying to include factors such as recent hot streaks, the number of all-stars or generational players on each team, and how to determine tie breaks between closely matched teams, with one of our suggestions being to factor in a home or away team. Now, with that, we'd like to leave you on one note moving forward, and that is, talent wins games, but teamwork and intelligence wins championships, and in this case, could predict a champion and win up to $1 billion. With that, we conclude our presentation and open the floor to any questions. Thank you.